Hello and welcome to episode 4 of our seminar, Falling in Space. In this episode, we're going to talk about Isaac Newton. He is the last scholar that we will talk about in this short history that I'm giving you, leading up to our understanding of motions of planets. Newton was born in 1642. That was almost to the day that Galileo died. Some people claim it is the same day, but that's disputed because of different calendars, etc. And Kepler had died 12 years earlier. Newton's father died before he was born, so he was initially raised by his mother. And when she remarried, he was handed over to his maternal grandmother. That's not a very excellent start in life for anyone, of course. But talking about this Galileo, Kepler, and now Newton, I thought it was illustrative to look at a little bit of a schematic of when these people lived, the people that we have talked about. And here you see, and which is really interesting, is that Galileo, Brahe, and Kepler were basically contemporaries. And Copernicus was clearly a generation before that. And now we're going to talk about Newton, and he is the next generation with respect to those three. So that's, I think, a good chronological overview to have in mind when we talk about all these people. We can talk for ages about Isaac Newton, but and there have been many biographies written and articles, etc. Here I'm going, of course, to only concentrate on these aspects which are relevant for our discussion about planetary motion. But as you will see, this is going to be very, very foundational for what we do today with spacecraft navigation. I want to mention a few episodes. It starts with in 1679, when he had discussions with Robert Hooke. Hooke was a famous polymath in England, also president of the Royal Society, before Kepler later got in that position. They had frequent fallouts between each other. Both of them, I think, were fairly complicated characters, to put it that way. Not easy to get along with. For Kepler, for Newton, that became worse when he grew older. But here was a discussion with Robert Hooke, and the importance here is that Hooke basically referred Newton to Kepler's laws, as we call them now, these statements that Kepler had made about elliptical motion of planets. That got Newton interested from the mathematical point of view. And one outcome of this discussion was that he said that he had proven for himself mathematically that these laws of Kepler actually are consistent with inverse square gravity. That is something I will explain in much more detail just in a bit. The point here is also quite interesting that Robert Hooke claimed that he had come up with this principle of inverse square law, as we call that in physics today. So that was already a dispute between those two people. But the key thing here in 1679 is that this was really when Newton's attention was drawn to Kepler's laws. And then he worked with John Flamsteed. Flamsteed is famous for his star catalogue. In 1680, there were two great comets, which was an enormous event because they were comets that were very bright and had a very long tail. They were even visible during daytime. And in that year, Newton had discussions with Flamsteed, who said, well, these are not two comets, this is one and the same comet, because the comet is on its way to the sun, is going around the sun and then reappearing after it has passed behind the sun. Newton initially didn't agree with this, but later he realized this was indeed a fact, that we now have a comet, which is a completely different object than a planet, and that also is going around the sun in probably a very elongated elliptical orbit. Newton published later about this using Flamsteed's observations that he got hold of somehow without Flamsteed knowing, and he didn't mention Flamsteed at all. But another example of how Newton dealt with his colleagues was almost plagiarism, per se. But anyway, let's not be too judgmental. I just want to mention the fact here that both Flamsteed and later Newton realized that here we have another celestial object, comets, that also go in an orbit around the sun, and that was a breakthrough. And then talking about comets, he worked also together with, for a considerable amount of time, with Edmund Halley. We know Halley because there's a comet named after him. Accomplished astronomer, Edmund Halley. There was another comet that was not the great comet of 1680, the comet of 1682, which Halley had observed at different points in its trajectory. And Halley had the idea that we may be able to reconstruct the orbit of that comet based on Kepler's elliptical laws. He discussed this with Newton. That revived that whole discussion about Kepler's laws for Newton. He couldn't find his notes that he originally had made when he was talking with Robert Hooke about this. And that led to a publication, which is in English called On the Motion of Objects in Orbit. And this really is the publication where he mathematically proved that Kepler was right with his laws. It's precisely correct. And this is why I'm so impressed with Kepler's laws. They were empirical. He had no way of proving it. But in the meantime, he had Newton had the mathematics available to him to do this mathematical interpretation of those laws. That's calculus. I'll come back to that. And he continued working with Halley, but in 1687, he had collected most of his work related to motions and what was to become gravity. And he published this in his majestic work, which is in English translated to Mathematical Principles of Natural Philosophy. Usually this is simply referred to as the Principia. Some people say Principia, which is also correct. It depends on which version of Latin, older Latin or more modern Latin you're applying. I prefer Principia, but that's personal. This was a work consisting of 3 books. The first one, the motu corporum, that was the same name basically as that separate publication that he had made about Kepler's laws. The reworking of that continued in the second book, and book 3 was a separate topic on the system of the world, and this really laid out his law of gravity and his ideas of gravity and how that connected to his laws of motion that he had described in the first book. This third book has also been published separately, and there were further editions of the whole series in 1713 and 1726. That was during in Newton's lifetime. I want to summarize the basic content of the Principia, but only pointing out the essential aspects in the context of our historic overview, leading to the methods of orbital mechanics that we have today to navigate spacecraft. So the first book talks about laws of motion. In high schools today, we teach these laws. There are 3 laws of motion by Newton. The first one states that if there's no force acting on an object, that object is either in uniform constant motion or it is stationary. This is not Newton, this is Galileo. He formulated that. Newton he leaned heavily on the foundations that Galileo had left behind, and also was using work by Descartes, which is a French philosopher and mathematician, who had in his own way interpreted Galileo's work, etc. So those were the starting points basically for Newton to work on these laws of motion. Galileo was really instrumental in that. The second law of motion, there he starts to figure out how can you change the motion of an object, the velocity, we call that acceleration, by applying a force on that object. He needed it because he needed to explain the motion of planets around the sun. And he realized that if a planet would not experience any force, it would just go in a straight line somewhere, but it would not go around the sun in what he called a curvilinear orbit. So there needed to be a force. And this is the second law. This introduces the concept of mass. I'll come back to what that really is. In my lectures, I usually make a reference to either a supermarket trolley. We didn't have those in Newton's days, but we have that now. If you want to change the speed of your trolley when you're shopping, either accelerate or decelerate, you need to apply a force on the handlebar. And we all know that that force is not very large that you need to make that thing move. If you compare it with your car on a horizontal street in neutral gear, if you want to make that move, that the car move, you need to apply considerable force. The difference between those two examples is the amount of mass that each of these objects have. The car has more mass than the supermarket trolley. This is essentially what Newton formulated in his second law. And he introduced concepts like momentum, which is he called quantity of motion, etc. And then he, in the third book, he formulated his law of gravitation as an inverse square law. I'll explain this in more detail in a bit. But that was the effect that he needed, and he called it gravitation. That would be a force acting on, for instance, the Earth going around the sun, a force acting on the Earth to make it go into this elliptic orbit in the sun. How else could the Earth go around in this curved trajectory? And without a force, it would disappear into space. So this was his thinking, and this is why where the law of gravitation and the laws of motion both come into play in trying to understand planetary motion. In order to formulate the or to prove the laws of Kepler, he needed a form of mathematics that today we call calculus. This was not new. It's not correct to say that Newton invented calculus, full stop. It goes back even to the principles go back to the classical Greek philosophers. And there was work done in the 17th century by various mathematicians about perfecting it. It has to do with the limit function that you can work with in infinitesimal small intervals. What Newton contributes to this aspect of mathematics, which consists of two operations, differentiation and integration. He realized that this was basically two sides of the same coin. These were connected. The one was the inverse of the other, actually. Interestingly, at practically the same time, there was in Germany a mathematician, Leibniz, who did exactly the same thing. He approached it from the integration part. He wanted to know what the area was under a curved graph, purely mathematical problem. You need integration for that with ever smaller intervals. And then connecting that to differentiation. Newton had done exactly the opposite. He started with differentiation and he worked the other way. It's very likely that they were completely independent of each other. Later, there was a fallout between the two that they blamed each other for plagiarism. Okay, so yeah, what's new in the world? But this is the very important contribution that Newton made in terms of this technique of calculus. Further perfectioning is putting it in basically in one model. Running ahead a little bit with this statement, I think, but this is a good point to make it, is that the whole Principia is basically a very complex mathematical treatise. It's not so much about physics, it's mathematics. And he realized, this is known from a correspondence that Newton had, that we still have, that he realized that he gave a mathematical explanation for planetary motion and for gravity that he needed. But he didn't explain why there was gravity. And in that discussion, he, with a certain sense of humor, he stated, "I leave that open to the consideration of my readers." In other words, I haven't got the foggiest idea. Why is there gravity? I can describe it mathematically and it seems to work. That's what I'm doing. Of course, I'm paraphrasing here. I can't quote Newton, but this is really the essence of it, and he realized it himself. I hope in a future seminar I will talk about the general theory of relativity, and then I'll get back to this problem that Newton left behind, because Albert Einstein solved it in his general theory of relativity. Let's talk about the law of gravitation in a little bit more detail. You see here on the right-hand side the formula. We talked about inverse square law. This is a principle which is now very often used in physics in many different phenomena. You have some form of radiation that originates in a point and it radiates equally in all directions. This is just a slice, what you see in this diagram here. At a certain distance, the flux, as we usually call it in physics, this radiation is spread out over a certain area. If you double the distance, then the area over which this radiation is being spread out, thinned out, is 4 times, 2 times 2 larger. That means that the intensity of this, whatever that radiation is, if you double the distance, it's 4 times, 2 squared times decreased. If you do it 3 times further, then the effect is 9, 3 squared. So he was convinced, and that was the original discussion with Robert Hooke as well, is that this gravitational effect would kind of tease out over distance according to this inverse square principle. And this is why you have the r squared, which is the distance between the two objects, let's say the Earth and the Sun, in the denominator. If this number gets larger, then the whole value becomes smaller. And it's the square, so this is why it's called an inverse square law. This holds for light, for sound waves, for electric fields, whatever. You can. It's being used, that concept, in many different forms. But here it's about gravity. And then he introduced the concept of mass. I'll come back to what mass is, or as far as we know. But it's an intrinsic property of an object. Think about a supermarket trolley and the car, this comparison I gave. The supermarket trolley has much less mass than the car has. And it's only because of that difference that the force that you need to apply to accelerate, to change the velocity, is different. That's the concept of mass, which you need as an intrinsic property of the sun and a planet, if you talk about planetary motion. He needed this force, as I said before, because of the first law of motion. If you don't apply force, the planet would go in a straight line and disappear. He needed a centripetal force, as he called it. Centripetal means seeking the center. If you literally translate it, this is a force directed to the center, which in a planetary case is the sun in its focal point in the ellipse. He needed that constant force in order to keep that planet to do as he, and I'm quoting here, as he said, to follow regular revolutions in curvilinear orbits. So this is where the laws of motion and law of gravity came in. He needed this concept of gravitation and mutual attracting force, to make it happen as a motion that was observed. The gravitational constant G, that's this here, that's just a number. Sometimes you get the impression that people are very kind of mystical about this. This is a constant of nature or something. This is a number that we need to match the units on both sides of the equation. This is mass. We express that in kg. So this would be kg squared. This is distance, that's in meters or in miles or yards, whatever you choose. It's a unit. These units are chosen arbitrarily, historically. But these units define the actual numbers in here. Here you have a force which is expressed in newtons. That's the unit for force. And in order to match these different fairly arbitrary units, you need a numerical constant in front of it to match that numerically. This really is the reason that you have a constant. There are many formulas in physics that have a constant. So, okay, these are some comments about the law of gravitation. It's actually surprisingly simple. Now let's ponder a little bit of the question about mass. It's actually surprisingly difficult to find an answer for that. What is it? Find the definition. But it has been used in different forms under different names, or even without naming it, by scholars all the way back to the ancient Greek, to Aristotle, Galileo. But they never defined what they meant. I can't recall what names they gave, if any. Newton had a name for it. He called it pondus. The quantity of matter is the measure of the same arising from its density and bulk conjointly. This is the definition that Newton gave. This has been criticized later, and in my view, correctly, because this is a kind of a circular reasoning. This is not a definition. You can't really do much with it. As we know, Einstein had the famous formula E is mc squared, where he showed that the mass is equivalent to energy. That's another approach to this concept of mass. But Einstein didn't really define what mass was either. It seems that people have been using this concept over all the ages without really worrying too much about a definition. Here's a publication, I found a recent publication by Frank Wilczek, and he thought about a definition for mass, and he started with subatomic level, with quarks and things. But here you see a quote from his paper where he basically concludes that we shouldn't be worried too much about defining mass, because we hardly actually use it as an independent property. I found that quite interesting to show you that we use this concept all the time, but we don't actually have a proper definition. Okay, now, so we have a fantastic mathematical framework for describing orbital motion given by Newton. This is the real importance, and that's you cannot overestimate, emphasize that, the importance of what Newton left behind. But if we want to apply this in reality, it's far more complex. And I'm naming here a few issues that make it much more complicated. The gravity formula is between two objects, like the Earth and the Sun, for instance. But we have many more objects in the solar system, and they must have their own effective gravity. Jupiter is the most massive planet in our solar system, so it's the first one to think of. The mass of Jupiter is more than the mass of all the other planets combined. So there is a gravitational effect between Jupiter and the Earth, for instance. So how do you accommodate for that? You have the Earth and the Sun, and then you have Jupiter doing his thing. Actually, Jupiter will also work on the Sun, have a gravitational effect, because Jupiter is in its own orbit around the Sun. This is what we call a three-body problem. Newton's formula is a two-body problem, can handle that, but if it's become a three-body problem, it becomes enormously more complex mathematically to work it out. And then you have more planets, of course, not only Jupiter, and maybe other objects, asteroids, moons. In theory, at least, all of them have their own gravitational contribution. So this becomes what we refer to in general as an n-body problem. You need advanced mathematical techniques to work that out. So that's one major complication. Another thing which Newton already had realized is that planets cannot be considered generally as perfect spheres and homogeneous distribution of their density or their mass. I mentioned that he had this concept. Let me go back. The shell theorem here, I mentioned this. That's what I'm talking about here. He formulated the principle that he could treat a planet and also the Sun as a perfect sphere, which has a homogeneous distribution inside, so that you could forget about the object itself and you just look at the center as a point, and you put the mass of that object in that point. And if you then look at the gravitational force between the two objects, the distance is the distance between the two centers. He needed that construction in order to make it happen in such a very simple form as the law of gravitation is. Only just one distance. We know now, and I'm pretty sure that Newton realized it as well, that reality may be more complex. Now we know for sure that it's far more complex. If you just take the Earth, it's certainly not a perfect sphere. It's flattened. It also has topography. You can just look outside to look at mountains and everything. It's irregular. The density distribution inside, the mass distribution inside is definitely not homogeneous. We have all kinds of underdensities and denser areas, etc. So now we talk about if you talk about the Earth sets up a gravity field, which is a three-dimensional field, which you need to just describe mathematically at length in a lot of detail, related to the mass distribution and the shape of the planet. You need to do the same for the Sun and any other object that you're working with. So that's another major complication with respect to the simple approach that Newton gave us the foundation of. And then that's not only gravity, there are other forces acting. We know that now because we are launching a spacecraft in space. If you look at the space stations that we have currently orbiting the Earth, their orbit decays. I'll come back to that when we get practical. Because, for instance, there's a little bit of air drag. There still is a little bit of atmosphere. at that altitude, which slows down the spacecraft. Actually, it's more accurate to say that the motion of the spacecraft loses energy, and that's why it lowers. So you need to maintain that orbit. There are also other surface forces acting, like solar radiation pressure, the photon pressure of sunlight, for instance, etc. So if you really go into navigating spacecraft, that's where I'm going here, it becomes a lot more complex. But the foundation that Newton gave us is definitely still the foundation. We still use Newtonian mechanics for what we do in space today. Only very rarely we will need to make some corrections for relativistic effects. An example is GPS satellites. They have accurate clocks on board. And according to relativity, both special and general, there's a concept called time dilation, two forms of time dilation. That means that the way we interpret the clock ticking in the satellite is different from on board of the satellite. So those are relativistic corrections that we need to make. But in general, for navigating spacecraft in space, Newton's foundation is totally acceptable still, just with these complications. Without advanced mathematics and without computers, we wouldn't be able to do this. So that's the good thing that we have those. One final statement, and I've used the term paradigm shift before when we talked about Kepler, where he broke away from this dogma that everything needs to be a circular motion, uniform motion. He said, no, it's an ellipse, and the velocity is varying in the orbit. That's what I call a paradigm shift, because it breaks away with a dogma which has been around for millennia. Here we have another paradigm shift, arguably even more important. I told you when we started with Aristotle that the concept was that there was a corruptible Earth realm where we are, where things are decaying and there's death, and there's birth, there's change all the time. And then in contrast, you have the heavenly realm, which is the incorruptible realm, where things are distinctly different. What Newton showed here with his laws of motion and his law of gravity applied to motion of planets is that the same laws of physics, if you call them that, the same mathematical models that we have to describe these motions are also the same laws that we need to describe motions here on Earth, like your supermarket trolley or your car. He did away here, and this was really the point in history that this happened. He did away with this dogma that we have an incorruptible heaven and we have corruptible Earth. No, he showed that we have a set of laws of physics that are valid in the heavens as well as down below here. And this is where the famous apple also comes in. I'm not sure if this is correct. I've never heard a plausible discussion about this or a conclusion about this, that he actually saw an apple falling and he realized, hey, this is gravity working. The apple falls towards the center of the Earth, wants to. And that's the same as the moon going around the Earth or the Earth going around the sun. I'm not sure, but even as a metaphor, this is exactly what I'm talking about here. The apple falls under the forces of nature, which are exactly the same as the forces acting on the planet when it's moving around the sun. So this is really, I think, a very important conclusion if we look at the contributions that Newton has made for us, that this was what I call a paradigm shift. Okay, I'll end the episode here. The next episode will do some practical work, which is very illustrative, and it's based on a thought experiment that Newton gave us.